Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video we're going to be building on Kc in year 1, and this time we're going to be looking at how do we calculate the amount of something at equilibrium if we're not actually given this directly using what's known as the ICE technique. And then that will allow us to work out Kc and its units just like you've been able to do in year 1. Now, if you haven't watched the year 1 Kc video, make sure you do that before watching this video to refresh all the stuff around Kc and equilibrium. So Kc is a measurement of the ratio of the products over the reactants. And it tells you how far an equilibrium has shifted. Has it shifted more towards the right-hand side or the left-hand side? The bigger the value of Kc, the more it shifted to the right-hand side or the product side. So if we were to take this equation and fit it to this idea, we would have our products on the top of the equation, and the stoichiometry or the molar ratios in your equation tells you what power to put these concentrations to, and then your reactants at the bottom of the equation. Now, depending on the state symbols of your reactants and products, you're either going to create a Kc expression for homogeneous reaction. That's where all the state symbols are the same. So often you'll see they're all aqueous, or they're all liquid, or they're all gases, and you include them. Now, if you have a heterogeneous situation of reactants and products, so they're different physical states, for example, if you have a solid as a reactant, then you do not include the different physical state in the expression. For example, if B was a solid and everything else was aqueous, our expression instead would look like this. So just be aware of that little nuance of detail if that arises. So going back to actually working out Kc, in first year Kc questions, you're given the concentrations of A, B, C, and D at equilibrium. So you just substitute or plug in those values here, and then obviously you times them to the power based on the molar ratios. That would then give you a magnitude or a value for Kc. You also then need to be able to work out the units of Kc. So first and foremost, we need to understand that square brackets means moles per decimeter cubed. So this is our units. So if we take this as our example, then our product line is going to be for C, moles per decimeter cubed. D is moles per decimeter cubed, but then that itself is cubed. And then we do the same process for the reactants. And then let's just simplify this all together. So our products is, there's 1 mole there, there's 3 moles there, so altogether mole 4. And then we've got dm minus 3, and then dm minus 3 cubed here. So that's minus 9 on this side, minus 3 there, so altogether minus 12. And we do the same process for the reactants. So again, dm minus 3 times 2 is minus 6, plus the minus 3 here makes that minus 9. And then the moles, we've got 1 there, and we've got 2 lots of moles here to make mole 3. Then what we need to do is cancel this down. So mole to the power of 3, mole 4, so we're left with 1 mole left over here. And we've got dm minus 9 here, and we've got dm minus 12 here, so that will cancel down, leaving us with the answer of mole dm minus 3 as the units for Kc. Obviously, this was a quick recap. If any of this didn't make any sense, go back to that year 1 video. Now, as mentioned earlier, if it's a year 1 type question, you're given A, B, C, and D, so it's a case of just plugging it in. But what if you're only given information about 1 or 2 of these? How can you work out the other reactant or product species at equilibrium? Let's look at a question that involves this. And what we're going to do is apply something known as the ICE method, as this will allow us to get the values for each of these different species at equilibrium from just 1 or 2 of them. So I'm just going to give you a moment to read through this as a typical question that you could get at year 2 level when dealing with Kc questions. Okay, so some pieces of information in here that is going to be really useful. First of all, we've got 0.40 moles of hydrogen and 0.3 moles of iodine gas. They're heated. Now this is what we mean by the start of the reaction or the initial part of the reaction. So we're going to just take that information and we're going to put it into this grid. Now this is known as the ICE method, initial, change and equilibrium. So what I'm going to do is, I've been given the equation here, I'm just going to put this in this row here. Then we're just going to fill out the information. So 0.40 of hydrogen, let's cross that out, that's really good practice in the exam. We've got 0.3 moles of iodine, let's cross that out. And then what we haven't been given is any information initially of hydrogen iodide. But obviously, at the beginning of a reaction, you never have any product, so that's going to be 0. You only have an amount of reactant. Now the second step is to extract information from the question in order to fill out this row here. So you can see from our question, we've been told that equilibrium is achieved, and then at equilibrium, we have 0.52 moles of the hydrogen iodide. Now you can see we have not been given any information about the quantity of hydrogen or iodide at equilibrium, but we have been given how much we started with. And this is where we're going to be using the ICE method in order to work out the number of moles of the hydrogen and iodine at equilibrium, and therefore we can work out Kc. So step 3 is all about working out the change row. But to do this, you need to find a column that we're going to call our way in. Now this column is a column with the information for both the initial and the equilibrium. So you can quite clearly see that hydrogen iodide, we can work out what the initial was because it's a product, so it's always 0. And we've got some information about the equilibrium. Now you can see the difference here is it is increasing. So we put a plus 0.52 moles. And however you want to do this, you just basically take the equilibrium and you minus the initial from it, and you can work out if you've got a plus or a minus. Obviously products are always going to increase in their amount, whereas on our reactant side we can already work out that these are going to decrease because they're reactants. Now step 4 is to then take this information from step 3 but use the molar ratio relationships to work out the change in the other columns that we need to fill out. Now what I mean by the molar ratio relationships is the molar ratios, or the stoichiometry, and how they are related. So here the ratio is 2 to 1 to 1. And that's all down to the fact that we've got 1 mole of hydrogen reacting with 1 mole of iodine to form 2 moles of hydrogen iodide. So plus 0.52 is our change for this column. Now, the way this column and this column are related is in the same relationship as 2 to a ratio of 1 is. If we wanted to go from here to here, we need to divide by 2. So I do exactly the same with this change here. So half of 0.52 is 0.26. We know it's a minus because it's a reactant. And obviously we have the same relationship with this column as we do with this column because it's 2 to 1. So this will also be 0.26. So step 5 is calculating the remaining 2 columns for the equilibrium. So we've got our initial, we've got our change, so we just need to do 0.4 minus 0.26. And then with this column here, we've got 0.30 minus 0.26, so we've got 0.04. Now you'll notice at this point here, we've been dealing with moles in the ICE part of our method. So this is 0.14 moles, 0.04 moles, 0.52 moles. However, Kc is always expressed as the concentration of products over the concentration of reactants. So we need to take these number of moles at equilibrium and convert them into concentration at equilibrium. Now the way we do that is by the equation N equals V times C. So if we want equilibrium in a concentration here, then we rearrange that, it's n divided by v. So we're going to take these as our n values and divide by the volume we're given in the question. Now here it says it's formed in a container of 1 decimeter cubed. So we just need to do 0.14 divided by 1 decimeter cubed. Just be aware, if it's in centimeter cubed, etc., we need this volume in decimeters, as our expression should always be moles per decimeter cubed. So obviously this is a nice case because it's just 1 decimeter cubed, and actually you could obviously get away with this, but it's important to remember this process because often you'll be given a volume that isn't 1 decimeter cubed. If you're not given a volume in the question, then just presume it is 1 decimeter cubed and just plug in these values here into your KC equation. Okay, so now we're at the stage we would be if we were given a year 1 question. They would already have generated these values for us. But year 2, you're expected to use this process to get to this stage. Now the 7th and final step includes quite a few little steps, but then you just need to work out KC and its units using these values. So in this example here, our KC expression should be hydrogen iodide squared, because of the molar ratio of 2, divided by the reactants hydrogen and iodine, which are both to the power of 1. Then we substitute in these values into this equation. You then express that we've got 48.3 as our KC value, and then because the units completely cancel out, it's unitless. Okay, so at this stage, these steps 1 to 7, I would make sure that you understand the procedure of how to tackle this. You understand how to lay out your question, and you pause the video here and see if you can remember those key steps before we have a look at 2 exam questions. So hopefully at this stage you're happy, you know the 7 steps. So have a look at this. This is an exam question. 6 marks usually for these types of questions, although if there's a bit more structure they can be worth less. But there's a lot going on here. What I want you to do is pause the video here and see if you can extract the correct information and apply it to the ICE method and take those 7 steps. So if you've had a go at this and you got the answer of 14.6 and the units being decimeter cubed 6 mole minus 2, and it doesn't matter if you got this the other way around, then you've got all 6 marks. If you haven't, we're going to look at this as a walkthrough. Okay, so we're just going to lay out the equation that we are given here into our column. So we've got our number of moles at initial, change and equilibrium, and then we've got our concentration at equilibrium as our 4th row. And then we put the carbon monoxide here, then we've got the 2 hydrogen, and then that is moving to form our methanol. Okay, then we need to start extracting out the information. So a chemist mixes together 0.114 and 0.152. So this is at the very beginning. So this is our initial. So we're going to just put these 2 reactants in. And obviously remembering that at the beginning of the reaction there's no product, so this is going to be 0. And then we're told the container is pressurized and sealed. The total volume is 200 centimeter cubed. Now that's going to be really useful later for when we work out equilibrium. We're told the mixture is heated to 500 Kelvin and then left to reach equilibrium. Now temperature, we don't need to have anything in here about temperature, so that is a little kind of distractor. We know it's reached equilibrium at this stage. The volume of the seal container is kept at 200 centimeter cubes, so that volume still stands at equilibrium. And then the chemist analysed the equilibrium mixture, so we're at this stage now, and finds that there is 0.052 moles of the methanol formed. Now that's all the information that's given, so we don't know anything about the equilibrium moles of carbon monoxide or hydrogen. So we're going to look at this. We've got our way in is this column because we've got 2 pieces of information, so that's how we know this one. It's a product, so it's increased by plus 0.052. Now, because of the molar ratios, and that's why I've copied this whole thing down because it just makes it really easy, this is a 1 to 2 to 1 ratio. So whilst this is increased by 0.052, this is going to increase by double that because if you go from 1 to 2, you have to times by 2. So you're going to do the same operation in this row. Remembering it's a reactant, so it's minus in front. So if we do that, that's minus 0.104. Whereas the change for carbon monoxide, well, that's 1-to-1 ratio, so that's going to be minus 0.052. So now we have enough information to work out the number of moles at equilibrium. So we do 0.114 minus 0.052, and that gives us 0.062. And then here we've got 0.152, and we're subtracting 0.104, which gives us 0.048. Now, if you put these into the Kc expression at this stage, you would have got the common mistake of 364 as your Kc value. And that means you've missed out the fact that you've got to convert this into a concentration. So we said earlier that we know the volume hasn't changed. It's 200 centimeter cubed. We need to get that into decimeters cubed. So we've got 0.2 decimeter cubed because we divide by 5,000. So we're going to take each of these as our n value, divide by this volume to give our equilibrium concentrations. At this stage, if you got to this part, you would have got 3 out of the 6 marks. All now that remains is that we get the Kc expression for this reaction. So we've got products on the top divided by the reactants, remembering to square the hydrogen because we've got 2 in front. Then we need to substitute in the values, so we've got 0.26, and our reactant values for carbon monoxide, we've got 0.31, and then we've got 0.24, but remembering from our expression we need to square this. If you then put that into a calculator, that gives you 14.6, and unit-wise, we've got moles per decimeter cube because there's just one concentration at the top, but we have 3 concentrations at the bottom, so that's cubed. We then cancel these down, so we remove that completely. That leaves us with 1 over mole 2 dm minus 6. But then we use index laws to reciprocate. And now that leaves us with this expression. So usually convention is to put the positive value first, the most positive, followed by the least positive, but mark schemes will accept either this form or the form here. So as this is a very common exam question that carries quite a lot of marks in terms of normally a 6 marker, I want you to pause the video here and have a go at this one. Okay, so first of all, Kc expression. So we should have that. Give yourself a mark if that was the case. The units of the equilibrium constant Kc, we have moles cubed dm minus 9, multiplying all of the products together. And then our reactants are like so. So the whole of this cancels down, leaving this is our expression. And then obviously we just need to invert this. And so we end up with dm cubed mole minus 1, or you can have the other version of this, which is mole minus 1 dm cubed. Now with this, you've then got 4 marks available for working out the equilibrium concentrations and then plugging it into your expression. So you should have this here, and then inputting in the information from the question. We fill out our initial row, fill out our equilibrium. This column is our weigh in, so we're just going to work out the change for that. As it's a 2-to-2 ratio, change in this is also going to be minus 0.2. On the product side, it's a 2-to-2 ratio here, so it's plus 0.2. And here, nitrogen monoxide to nitrogen is 2-to-1. So this is going to be, you'd have to divide that by 2 to get the ratio right. So we're going to divide this by 2, so it's going to be plus 0.1. And then we use this information to fill out this row. So that's our number of moles at equilibrium. We now need to get this into concentration, and remembering concentration is number of moles over volume. Our volume is given up here as 1 decimeter cubed, so basically these all stay the same in terms of moles per decimeter cubed, which is a nice situation. Then what we do is we plug these values into our expression here. Put that in the calculator and you should get 0.95. So you can see that by using this ICE method and this way of laying out the question, you can make a 6-mark question really manageable. And it just comes with loads of practice and making sure that you keep revisiting this procedure so that it's habitual. Okay, so in this video we've been looking at calculating quantities at equilibrium in order to work out Kc. If you found the video useful, ensure that you like it and then ensure that you subscribe to the channel for new videos as and when they're uploaded.